Hello everyone, welcome to the class. Today we will start module number 9. In this module we have several topics. The first one is Fresnel half period zones, and thereafter we will talk about vibration curve, that would be followed by zone plates, and then we will discuss about diffraction at a straight edge, then diffraction of a plane wave by a long narrow slit, and at last we will see how the Fresnel diffraction pattern make transit to the Fraunhofer region. Since this is the first lecture on the diffraction, therefore, we must revisit what we studied or what are the conditions in Fraunhofer design. In Fraunhofer domain, the diffracting system was relatively small. Okay? Relatively small means its size was smaller than the distance between screen plane and the source plane, and the point of observation was very distant. Okay, this is what is the point, or let me say it like this. In Fraunhofer configuration, the diffracting system was relatively small and the point of observation was very distant. Okay, because in the very first class of diffraction, where we introduce Fresnel and Fraunhofer categories, we discussed that in Fraunhofer domain, both the source and the point of observation on observation plane, they must be at infinity from the diffracting plane or from the diffracting element. Okay, this was the condition which was imposed by Fraunhofer diffraction. While in Fresnel domain, we deal with the near field region, which extend right up to the diffracting element itself, and any approximation would therefore be inappropriate. Okay. The approximation which we considered in Fraunhofer diffraction was that the distances distances of the source and the screen from the aperture plane must be infinity, but in Fresnel domain we will not rely on this approximation. We may even go much closer to the diffracting element. Okay. Now, with this we will also have to revisit the concept introduced by Huygens-Fresnel principle. Okay. Now, what are the points which need to be re-examined? At any instant, every point on the primary wave front is envisioned as a continuous emitter of spherical secondary wavelets. That was the basic principle or basic statement proposed by Huygens. Okay. Now, Huygens again said that each wavelet radiated uniformly in all directions in addition to generating an ongoing wave. There would also be a reverse wave travelling back towards the source. Okay. And this is something which we do not see in our daily life here, because suppose we have a wave front and each point on the wave front it emits a spherical wave front. Now, Huygens said that we just draw an envelope on these secondary wave front, and this envelope will give a new position of the wave front. Okay. But since the wave is emitted by these point sources on the primary wave front, they are also propagating in the backward direction, and therefore, if you draw envelope here, then you will see that the wave is propagating in forward direction as well as in the backward direction. This is quite contrary to the usual observation, because we know that the wave propagate in the forward direction. Okay. Therefore, this point is a point of concern. Okay. Because no such wave is found experimentally. So, we must somehow modify the radiation pattern of the secondary emitter, and this modification was introduced by Fresnel. Okay. And the new principle is called Huygens-Fresnel principle, where Fresnel introduced that this emitting wave, they propagate in the forward direction only, and he also said that they interfere, and therefore, the Huygens-Fresnel principle is now can explain diffraction. Okay. but exact mathematical formulation came quite later, and it was given by Kirchhoff. Now, Kirchhoff, what he said is that he mathematically formulated a function which is called obliquity or inclination factor. Okay. K theta is called obliquity or inclination factor, and it is defined as 1 by 2 1 plus cos theta, okay, or 1 plus cos theta by 2, as is given by equation number 1. And this obliquity factor dictates the direction of propagation of wave. Okay. Now, here the angle theta is the angle made with the normal to the primary wave front k. Okay. Suppose this is our wave front, and this is the k vector direction, and this is the point of observation P, then this angle is theta. Okay. And of course, from expression 1 we can easily see that this has a maximum value when theta is equal to 0, and when theta is equal to 0 we have k 0 is equal to 1. Okay. It means all the energy will propagate in the forward direction, but if you see the propagation in backward direction, then what you find is that when theta is equal to pi, then k pi is equal to 0. It means nothing is propagating in the backward direction. This was the corrections which were introduced later in the Huygens principle, and the limitations which the Huygens principle had, it was removed just by introduction of this obliquity or inclination factor. Okay. Now, we will examine the free propagation of a spherical monochromatic wave emitted from a point source. Okay, but before that, let us see how does this obliquity factor look like. Here in this figure, you see that we have a point source, and then these are the wave fronts, spherical wave fronts, which are being emitted through this point source. Okay. Now, to decides the shape or the direction of propagation of the wave and the shape of the new wave front, following Huygens principle, we take large number of secondary point sources on a wave front, and this from these secondary point sources we assume that new wavelets are being generated, and then we draw a common envelope on these all secondary wavelets. Okay. And this is how the wave propagate. Now, this is the direction of k, which is perpendicular to the wave front, and P is the point of observation, and the angle between this line and the k direction is theta angle. Okay. And this shaded region shows the part of the energy which will go in different direction, which will go in different theta directions. Okay. Now, if you plot k theta with respect to theta, then you see this kind of variation. Okay. Then obliquity factor show this type of variation, and now you see that in the forward direction its value is 1, while in the backward direction its value is 0. It means that most of the energy will propagate in the forward direction, a part will go in other theta direction, but in the backward direction no energy will propagate, the wave will not propagate in the backward direction. Now, we will consider a wave propagation in free space. Okay. Now, if the Huygens-Fresnel principle is correct, we should be able to add up the secondary wavelets arriving at point P. Okay. We have a source here, and from this source a wave is being emitted, and at the point of observation P it is being regarded, it is being observed. Okay. Now, the principle says that we should be able to add up the secondary wavelets arriving at point of observation P. The spherical surface corresponds to the primary wave front at some arbitrary time t prime after it has been emitted from S at time t is equal to 0. It means that suppose we have a point source which is emitting a spherical wave front, and this wave front is recorded at time t prime, and since it takes some time for wave to reach at this position, therefore, it must have started at some earlier time, and we assume the wave start from point source S at time t is equal to 0, and then it reaches to this position at time t is equal to t prime. With this, the disturbance having radius rho, say this radius of this spherical wavefront is rho, this can be represented by equation number 2, which says the field E is equal to epsilon naught by rho cos omega t prime minus k rho. Rho is the radius of this wavefront. Now, what we do is that suppose we have a point of observation P here and we divide the wavefront in a number of annular regions. How to do this? This is clearly depicted in this figure. Now, in this figure you see we have a point source S, and at a time t prime the point source has this wavefront, okay, and the radius of this sphere is rho, okay, this is the radius. Now, what we do is that from the point of observation P we draw various spheres of radius r naught plus lambda by 2, and then r naught plus lambda, and then r naught plus 3 lambda by 2, and so on. Okay. From point P we now draw various spheres of these radius, okay, and these radii are varying by lambda by 2 at each step. Okay. The consecutive are at the adjacent sphere which are centered at P, they vary by lambda by 2 in their radii. Okay. Now, when we draw the spheres, they will cut this spherical wavefront in different annular regions which are depicted here. The first sphere will generate this shaded region which we name as Z1, the second sphere will generate this less shaded region which we name as Z2, the third sphere will generate this dark shaded region which we call Z3. Okay. And this point is the nearest point on the wavefront from point of observation P, which is at a distance r naught. Okay. The boundaries of the various regions correspond to intersections of the wavefront with a series of spheres centered at P of radius r naught plus lambda by 2, r naught plus lambda, r naught plus 3 lambda by 2, and so forth. And these regions are known as Fresnel or half period zone. Okay. The word half period comes from the lambda by 2 difference in the radii of adjacent sphere, okay, because lambda by 2 is half of the period, isn't the full period, the full wavelength is lambda, but half period is lambda by 2. Therefore, these zones are called half period zone or Fresnel zone. Okay. Now, what we do is that we pick some lth zone, say there is n number of zones starting from 1, and we pick one of these zone and say this zone is lth zone. Okay. Now, lth zone is situated between L minus nth zone and L minus 1th zone and L plus 1th zone. Okay. It is between L minus 1 and L plus 1 zone. Okay. This is in between these two zones. Now, we assume that this zone has boundaries which are, let me explain it here. Suppose this is the zone which we are interested in. Okay, I am shading this zone, and the area of this zone is ds. Okay. As this point, which is point O, which is the nearest point from the point of observation, is at a distance r naught, we assume that this annular ring, the lower portion of this annular ring at this point particularly is at a distance small r from point of observation P, while the upper point here is at a distance r plus delta r from point of observation P. Okay. Now, this distance of course would be rho, yeah, this distance would be rho, this angle say is phi and this angle is d phi. Okay. Now, I can redraw this figure because it is too much now in this figure. Let me redraw it. Now, say this is our point S and this is our point P, okay, and the annular region is somewhere here. Okay. Okay. This is the annular region which we are interested in, and this annular region has area ds. Of course, this distance is rho, okay, which is the center O, and this distance is r naught as depicted in the figure, okay, this figure. Now, say this distance is r, and from the upper portion of this annular region it is r plus dr, okay, and this is rho because this is whole all of this annular region is on the surface of the sphere. Therefore, all points of the annular region would be at distance rho from the source, okay, because source is the center of the sphere. Now, say this angle is phi and this angle is d phi. Okay. With this we can easily calculate the area element ds. And one more point, this is wave vector k direction. Therefore, this angle would be the angle theta. Okay. Now, hope this picture is quite clear to you all. Now, in this picture you can see that the source S is effectively at a distance rho plus r naught from the point of observation P. Therefore, what we did is that we defined a ring shaped differential area element ds, and all the point sources within ds are coherent. Okay, since the area element ds is very thin, okay, therefore, we assume that all the point sources which are situated on this area element, they are coherent, and we also assume that each of these point sources radiates in phase with the primary wave. Okay. This is our primary wave, okay, and the sources are here in this small area element, and it is also here, and since the thickness is very small, we are imposing two conditions, or we are assuming that they are coherently emitting. Whatever they are emitting, everything is in phase with the primary wave. The secondary wavelets means the emission which are coming from the point sources sitting on this area element. Yeah, the secondary wavelets travel a distance r to reach at P, yeah, which is very much clear from this figure. You see that. Let me pick a different color. You see that this distance is r, and therefore, the secondary wavelets, okay, which are being emitted from point sources sitting on this area element, they travel a distance small r to reach at point P. Now, we also assume by the time they reach there, it is time t. Okay, they reach at a time t is equal to t. Made this statement that all the point sources on the area element is coherent and they are radiating in phase. Okay. Therefore, all the wave or all the light which reach at point P from this area element would be in same phase. Okay. And how to calculate this phase? This phase would be omega t minus k into total distance travel. And what is the distance travel here? Distance travel would be this distance. Okay. And what is this distance? It is rho plus r naught, isn't? But this distance is the horizontal distance, but our area element is a bit shifted. Okay. It is an annular ring which is away from point O, which is sitting at the center. Therefore, the new distance is r, okay, and the overall phase therefore would be omega t minus k rho plus r. Okay. This should be the phase of all the wave reaching at point of observation P. and this is what is written here. Therefore, all these wavelets arrive at point P with phase omega t minus k rho plus r, okay, where r is variable. If you keep varying the annular ring, r will vary, okay, and the amplitude of the primary wave at a distance rho from S is given by epsilon naught by rho. Okay, this we have already studied, because in case of a spherical wave, the distance comes in the denominator of the amplitude. Okay. Therefore, we define source strength per unit area here too, and the source strength per unit area of the secondary emitters on ds therefore will be equal to q epsilon naught by rho. Okay. But epsilon naught by rho is the amplitude of the primary wave, which is at a distance rho from the source. We are just modifying this amplitude by some multiplication factor q, and which we do not define at this point. Okay. We assume that the amplitude of the primary wave would be modified in case of secondary emitters. Okay. But let us assume that this modification is taken care of by this multiplication factor q, where q is some constant. Okay. Now, we will move ahead with this. The contribution to the optical disturbance at point P from the secondary source on ds is therefore be equal to k epsilon a by r. Epsilon a is defined here in equation number 3, which is source strength per unit area, and then the phase part cos omega t minus k rho plus r, okay, into ds. Okay. Epsilon a is source strength per unit area, but for area ds we will have to multiply epsilon a with ds to get the complete source strength information. Okay. K is obliquity factor here, and which dictates the variation of dE with theta, okay, because the wave propagate in all possible direction, then it decides what amplitude goes in which direction. Therefore, we have multiplied it following Huygens-Fresnel principle. Okay. The obliquity factor must vary slowly and may be assumed to be constant over a single Fresnel zone. Why? Because Fresnel zone is very thin. Okay. Each Fresnel zone, the Fresnel zone is defined by some annular ring, and this annular ring, the inner circle is at a distance r, say r prime, and outer circle is at a distance r prime plus lambda by 2. Therefore, the effective difference between the two distances is lambda by 2, and this says that the width of this ring would be very small, and therefore, we may assume that theta does not vary over a single Fresnel zone or over a single annular ring, and if theta does not vary, then k also remains constant. Okay. Therefore, we can assume that obliquity factor q is almost constant, it is very slowly. Okay. Now, we calculate the area element. The area element from this figure can easily be calculated. You know, the periphery is 2 pi r, and r is here this distance, okay, and this distance is nothing but rho sin phi. Okay. Once rho psi phi is known, then the area would be equal to 2 pi r, r is rho sin phi, and then the width of this strip, the width of this annular region. What would be the width? It would be angle into radius. Okay. Angle is here d phi, yeah, angle is d phi and radius is rho, and this is how the area of the annular region is calculated. Okay, and this is what exactly is written here. D phi into rho is the width of the ring, width of the annular portion, and 2 pi rho sin phi is the periphery, okay, the periphery of the circle. Now, with this we will also do some mathematics in this triangle. Yeah. Now, suppose this is a triangle here, that is a bigger triangle. Okay. Say it is A, this is point B and this is point C. In triangle ABC, let us redefine A. So, let us pick a smaller triangle here. Now, we pick a triangle which is starting from here, it goes to point source S and then point P and then coming back to this. Okay. The tip of the triangle is at the inner circle. Say this is point A, here it is point S and here it is point P. Yeah. Now, in triangle ASP, from triangle ASP, okay, using very basic trigonometry you can write equation number 6, where r square, which is this AP distance, yeah, this is point A, AP is r. Then this triangle r square would be rho square. Okay, I read right here. This is ASP, this distance is rho plus r naught, this distance is rho and this distance is your r. Okay, and this is our phi angle. Now, in this ASP triangle we can use basic trigonometry and get this relation between all the sides of the triangle. Okay, this triangle all the sides are given and one angle is given. Therefore, r square would be rho square plus r naught whole square minus 2 rho plus r naught into cos phi. Now, if you differentiate this relation, this equation number 6, if you differentiate it, then you get this 2 r dr is equal to 2 rho in bracket rho plus r naught sin phi d phi, where r naught and rho are held constant because they are fixed numbers. Okay. Now, from here we can calculate the expression of d phi, and with this d phi is then substituted back in equation number 5. Okay. Here we will substitute for d phi, okay, which is given in equation number 7, and from there using equation 7, equation 5 takes this form. Okay. This is from equation 5, and we substitute this value of ds in the expression of the field. Okay. Now, the expression of the field is given here, equation number 4. Okay. Now, the value of ds is substituted in equation number 4, and equation number 4 is written for some area element ds. Now, we assume this area element, as I said before, is Lth zone, Lth Fresnel zone or Lth half period zone. Okay. Then, to consider all the point sources in this Lth half period zone, we integrate the equation from RL minus 1 to RL, okay, because if this is the half period zone, the shaded region which we are considering in our discussion, and we name this as Lth zone, then say this is point of observation P, then this distance is r naught, okay, and this is Lth zone. Therefore, this distance would be r naught plus lambda by 2 into L minus 1, okay, and this distance would be r naught plus lambda by 2 into L, okay, and we name these distances as RL and RL minus 1. Okay. With this, we can safely put these two limits in this integral in equation number 9, and then after integration we get equation number 10, where RL minus 1, as I said before, is equal to R naught L minus 1 lambda by 2, and RL is R naught L lambda by 2, which is what I wrote here. Now, with this substitution, equation number 10 reduces to equation number 11. and here you see we get a minus 1 to the power L plus 1. Okay. It means if you vary L, the sign of EL also varies. Okay. The amplitude of EL alternates between positive and negative values, and it depends whether L is odd or even. The rest of the term are shown here. KL is the obliquity factor for LH zone, epsilon A source strength per unit area, rho is the radius of the spherical wave front, lambda is the wavelength, all the things we have already defined here. Now, there are few points which we can draw from this expression. The contributions from the adjacent zones are out of phase and tend to cancel. Okay, because from in equation 11 we see that EL alternates between positive and negative values. If L is equal to 1, then EL is positive, if L is equal to 2, then EL is negative. It means the adjacent zones are 180 degree out of phase. Okay. Therefore, the contribution from the adjacent zones are out of phase and tend to cancel, and each zones are very thin. Therefore, the amplitude of the wave received at point P emanating from point sources sitting on these zones, they are almost equal, but opposite in sign, therefore, they cancel each other. Okay. But they do not cancel perfectly. Why? Because as you increase L, the angle theta increases, and therefore, the obliquity factor K, it decreases. Okay. Therefore, the obliquity factor makes a crucial difference as L increases, theta increases and K decreases, because K is equal to 1 plus cos theta by 2. Therefore, with increasing theta, K decreases. Okay. Therefore, the contribution from each zone as you move up, as you go increase L, it successively reduces. Okay. And therefore, the successive contribution do not in fact completely cancel each other. Okay. The contributions weaken as you go up, as you increase L, but this ratio EL by KL is independent of any position variables. Why? Because although the areas of each zone are almost equal, they do increase slightly as L increases. Okay. Because if you increase L, then the radius of this zone would be larger. Yeah, it's a rho sin theta, and the radius of these zones are rho sin theta. Yeah, we defined these zones like this, and this distance was rho. Okay, and this is phi. Then the radius of zone is rho sin phi, or if you talk in terms of theta, then 2 this radius is increasing. Okay. Therefore, as you increase L, the area of these zones slightly increases, and since the area of these zones are increasing, the number of emitters which are sitting on a particular zone, it also increases with L. Okay. I repeat, although the area of each zone are almost equal, they do increase slightly as L increases, which means an increased number of emitters, but the average distance from each zone to P also increases. Yeah, because as you increase this ring radius, that this distance also increases, the distance from the point of observation P, and this increase is such that EL upon KL remains constant. Okay. Number of emitters are increasing, therefore, EL should increase. Okay. But alongside theta is also increasing, therefore, EL upon KL remains constant. Now, once we have calculated the disturbance at point of observation P due to some arbitrary annular ring, and then we can calculate the total contribution at the point of observation P, and this total contribution comes from all the annular rings, from all the zone plates. Okay. Now, since we have done it for lth zone, we can vary L, and then we will get from first zone, then second zone, then third zone, and then the last zone, the mth zone. Okay, we name the last zone as mth zone. Now, this is the wave front which was emitted by point source S, and this is how we splitted the zones. Okay. This is your first zone, this is second zone, this is third zone, this is fourth zone, and at the center here there is a point O. Now, similarly, if you keep increasing, then these zones will also be here too, yeah, and say this point is named as O prime, and this is our last zone, our mth zone. Okay. This is your m minus 1th zone, and so on. Yeah, this is how the number decreases here, and it is increasing from in this direction. The point source is here. Okay, and these zones are very thin. Then we calculate the contribution from each zone and sum them up, and this would be the resultant optical disturbance at point of observation P. We also know that in the expression of EL, in this equation number 11, you see that amplitude of EL alternates between positive and negative value. Therefore, we will also enjoy this knowledge, and we will implement it in equation number 12, and therefore, the 12 modifies to 13, which now have alternate sign before all field contributions, all disturbance contribution. E1 is positive while E2 is negative, E3 is positive while E4 is negative, and so on and so forth. But we do not know whether the number of zones, the total number of zones is even or odd. Therefore, we put both plus and minus here, it is not decided yet. Okay. But now, let us consider a case when m, the total number of zone, is odd. Now, this series which is given in equation number 13, this series can be arranged in two ways. Okay. Now, the first way is E is equal to E1 by 2, like what we did is that we were having E1 and then E2. This is how the things were written in equation number 13. Okay. But here what we do is that we split E in two part. Okay. We write as, sorry, it is E1 by 2 and then E1 by 2. Similarly, E2, no, and for E2 we just write E2, we do not split it, but for E3 we again perform the splitting and we write it like this. Now, we have one term here in this bracket in which we have contribution from first zone, contribution from third zone, as well as the contribution from the second zone. The full contribution of second zone is embedded here in this middle term, but the contribution from the first and third zone is considered partially here, because you are seeing that in the denominator we have a term 2. It means half of the contribution from the first zone and half of the contribution from the third zone is there within this bracketed term. Okay, and this is performed for all the coming terms here. Now, if you write this equation number 13 in this form, then you get first term here in the bracket, the half of the first term, the second term, and half of the third. Similarly, this bracket. Okay, and since the number of term be assumed as odd, it means we will be left with Em by 2, mod of Em by 2 here. Okay, since the number of term is odd, you see that first term is split in 2, the second term is left as it is, third term is split in 2. Therefore, the last term would again be split in 2. Okay, all odd terms are split in 2, therefore, last term will be again split in 2, and we will have this bracketed terms before the last term. Okay. Now, alternatively we can also write it this way. Okay. The field E is first term, and now split the second term. Okay, and perform the same things with the second, third and fourth term. Okay, and then proceed in a similar manner. Okay. In this case, the last term would not be splitted, okay, because here the odd terms remain as it is. Okay. Therefore, EM is kept as it is not splitted, because the number of terms in this series is assumed to be odd. Now, with this again there are two possibilities. Okay. With either of the last two series there are two possibilities. Either EL, a particular field, is greater than the arithmetic mean of its two nearest neighbor, that are EL minus 1 and EL plus 1, or it is less than that mean. Okay, what it means to say is that either EL would be larger than the mean of EL minus 1 and EL plus 1, or it would be smaller than mean of EL minus 1 and EL plus 1. If EL is larger than the mean of EL minus 1 and EL plus 1, in that particular case each bracketed term is negative. Okay, let us go back into equation number 14. Let us look particularly in this term. Okay, here we assume that E2 is larger than the average of E1 and E3. Okay, if E2 is larger, then each bracketed term here will produce a negative quantity. Okay, this would again be a negative quantity. Similarly, the last bracket will also be a negative quantity. Therefore, the resultant disturbance at P would be smaller than this term plus this term. Okay, because all the terms are bracketed, these are only the two free terms, the first one and last one. Okay, and since we are in equation 14, in terms E1 by 2 and EM by 2, we are only adding some negative terms. Since all the bracketed terms are negative, okay, because we have assumed that EL is larger than the average of the two, therefore, capital E from equation number 14, it would be less than E1 by 2 plus EM by 2. I repeat, we have a series where this is the first term and this is the last term. Okay. And in this series, apart from these two terms, we have lot many negative terms. Okay. And once these negative terms or these terms are subtracted from this first and last term, we get E. Therefore, E must be smaller than E1 by 2 plus EM by 2, and this is what is written here. Okay. If you do not add those negative term, then E will be smaller than E1 by 2 plus EM by 2. Similarly, from equation number 15, let us go to equation number 15 now. Now, we have assumed that the middle term is larger than the rest of the two in all the bracketed term. Okay. Therefore, here we get a again negative term, this bracket term will also give a negative term, this bracketed term will also give a negative term. All these terms are negative, but before all these negative term we have minus sign. Okay. Therefore, all these bracketed term would be positive. Okay. Now, what are the free terms in the equation number 15 which do not have any bracket? E1 mod of E1 minus mod of E2 by 2 minus mod of EM minus 1 by 2 and mod of EM. These four terms, they do not have any bracket, and all these bracketed term are positive. Okay. Now, if you develop a relation between or equality between E, the total resultant field, and these four terms which do not have any bracket, then we will get this relation. E is larger than E1 minus mod of E2 by 2 minus mod of EM minus 1 by 2 plus mod of EM. Why? Because from the right hand side we have removed some positive term, and therefore, E must be larger than this term. Okay. Had we have added those positive term, E would have been equal to this plus those positive term, but since those positive terms are gone, we have removed them, therefore, E must be larger than these terms. Okay. Once these things are understood, then we can proceed further, and we know that the obliquity factor, the maximum value of obliquity factor is 1 and the minimum value is 0. Okay. And this obliquity factor goes from 1 to 0 over a large angle. Okay. When angle theta is equal to 0, we have a k is equal to 1, and when theta is very large, then we get k is equal to 0. It means that obliquity factor goes from 0 to 1 over a great many zones. Okay, we have to consider very large number of zones for this to realize this change in k, obliquity factor. Okay. Therefore, we can neglect any variation between adjacent zone. It means that since zone area is almost, the two adjacent zone area is almost same, therefore, we can assume the adjacent zone, they contribute equally at the point of observation P. Okay. And therefore, we can roughly assume that mod of E1 is equal to, almost equal to mod of E2, or mod of Em minus 1 is roughly equal to mod of Em. With this equation, it reduces to equation number 19, because now we assume that E1 is, mod of E1 is equal to mod of E2, then from here we will get mod of E1 by 2. Similarly, from here we will get mod of Em by 2. Okay. And with this we get a modified version of equation number 18, which is equation number 19, where which says E is larger than mod of E1 by 2 plus mod of Em by 2. Similarly, we can conclude from equation 17 and 19. Okay. 17 is here, okay, and 19 is here. Now, you see that once E is less than mod of E1 by 2 plus mod of Em by 2, and once it is larger than mod of E1 by 2 and mod of Em by 2. With those two equations, we can conclude that E is almost equal to mod of E1 by 2 plus mod of Em by 2. Now, for arriving at equation number 20, we have assumed that field due to the lth zone is larger than the average of fields due to the adjacent zones. Now, we assume opposite, if the field reaching at point P is smaller than the average of the adjacent zone. In this case too, if we follow the same procedure, and if the last term m is even, in equation number 13, equation number 13 is this our main equation. Yeah, this is our equation number 13. Now, if we assume that m is even and then follow the same procedure, then we get this. Okay, I repeat, from equation 17 and 19 we get this relation, and the same result would be obtained when we assume that contribution from the lth zone is less than the average of the adjacent zone, then too we get the same result. And on top of this, if we consider our second case wherein m is even, then from equation number 13, after repeating all the procedures which we did in our last few slides, we get equation number 22. Okay. Therefore, equation number 20 and equation number 22 are our final results when m is odd and when m is even respectively. Okay. This is for m even and this is for m odd. Let us now talk about obliquity factor and its role in deciding the final expression of the resultant field due to all the half period zone at point of observation P. Now, Fresnel conjectured that the obliquity factor was such that the last contributing zone occurred at theta is equal to 90 degree. Okay. He started with theta 0 and he assumed that when theta is equal to 90 degree, the last zone appear, and therefore, for theta 90 the k becomes 0. Okay. For k to be 0, theta should be between or equal to pi by 2 and pi. Okay. This is the range for the theta which was given for k to be 0. With this, the equation number 20 and 22, which is here, they both reduces to E almost equal to mod of E1 by 2. We can neglect this reaches to 0. Why? Because this is the last half period zone, and for this theta is between this range. Okay. For EM, theta lies between pi by 2 and pi, and therefore, the obliquity factor goes to 0, which is a multiplication factor in the expression of EM, and therefore, EM goes to 0. Okay. And which is what exactly is written here. When mod of EM1 goes to 0 because of Km pi by 2 is equal to 0. When this happens, then E is equal to mod of E1 by 2. Okay. But Kirchhoff corrected the expression of obliquity factor. He said that obliquity factor goes to 0 when theta is equal to pi. Okay. And when will theta be equal to pi? Theta will be equal to pi for the last half period zone, which is this zone. And for this zone, you can easily see that theta is almost equal to pi, it would be near to pi. Okay. The last period zone will contain O prime, okay, which is diagonally opposite to O. Okay. With this, let us again see equation number 20 and 22. Now, alternatively, using Kirchhoff correct obliquity factor for the last zone surrounding O prime, theta approaches to pi, and with theta pi 2, this expression of obliquity factor, which is 1 plus cos theta by 2, it again goes to 0 for theta is equal to pi. Okay. It means mod of EM would be 0, either you apply Huygens-Fresnel principle or the Kirchhoff modification. Then the final resultant disturbance and at the point of observation P is therefore equal to mod of E1 by 2. Now, we see that we have a point source which emits a spherical wave front, and then we splitted this spherical wave front in large number of annular ring. We calculated the contribution from all the rings at the point of observation P, and what we found is that the total contribution at point of observation P is half of the contribution of the first annular ring or the first half period zone. Okay. Thus, the optical disturbance generated by the entire unobstructed wave front is approximately equal to 1/2 the contribution from the first zone. Okay. Rest got cancelled among themselves. The phase is such that rest do not contribute. Okay. Now, this is a quite cumbersome, complicated analysis. Okay. What we did is that we considered a point source and we considered a point of observation P, and we let the wave propagate from this point source to the point of observation P, and then following this analysis we calculated the field at point P. But there is a very straightforward way of calculating the field. We know what would be the field at point of observation P from a point source S, which is separated by certain distance. Okay. And what is this traditional way? This is this expression, the amplitude by the radial distance into phase part cos omega t minus k rho plus r naught, because effectively we have a source and we have a point of observation, and the spherical wave front start from a point source, and this distance is rho plus r naught. Okay. Rho is the radius of this wave front, okay, and r naught is this distance. Now, the total distance is rho plus r naught. Then if you are asked to calculate the field at a point P, which is at a rho plus r naught distance, use the simple formulation. E would be equal to amplitude by radial distance into cosine function, and then the phase part omega t minus k rho plus r naught. This is the expression which we have used multiple times. Now, this equation number 24 must be equal to the expression which we calculated, which we derived using Fresnel half period zone. Okay, but half period, this from Fresnel half period zone we know that the resultant E would be E1 by 2. What is E1 then? Okay, the E1 is given by here. Let us go to equation number 23. This is the final expression from half period zone calculation. Okay, E is E1 by 2, and what is E1 to have a expression of E1, let us go back to the general expression of EL. Okay, this is equation number 11 is the expression. Okay, here in we will just replace L by 1. Okay, in place of L we will write 1, and then we will write rest of the term on the right hand side, and this will give the expression of E1, and then we will half this expression, we will just divide it by 2, and this will give us the resultant field at a point of observation P. Okay, let us do this, and after doing this we get this expression. Okay, the disturbance synthesized from secondary wavelets, equation 11 and equation 23 is this, equation number 25. Okay, equation 23 is the expression of EL. Okay, and equation 11 is equal to, almost equal to mod of E1 by 2, and with these two equations we can get equation number 25 very easily. Now, this equation number 25 must be identical with equation number 24, but let us compare now. Okay, we will compare these two equations must however be exactly equivalent, okay, because they are saying the same thing, and we interpret the constant in equation number 25 to make them so. Okay. If you remember, while introducing the strength of the source per unit area, we introduced some constant Q, okay, which is unknown, and K is also there, it is K1, yeah, it is not L. Okay, K1 is also here, and we will also calculate the value of K here by just by comparing equation number 24 and 25. Okay, let us compare them. Let us compare the amplitude part. Here amplitude is epsilon naught by rho plus r naught, and here amplitude is K1 epsilon a rho lambda upon rho plus r naught. Okay, let us compare them with this. Sorry, it is r naught. Okay, epsilon naught, this is the amplitude here. Now, this amplitude must be equal to the amplitude of equation number 24. Okay. Now, since we are talking about the first half period zone, for first half period zone, you know, the angle is very small, it is very close to 0. Therefore, we prefer to have obliquity factor equal to 1 in the forward direction, and that is K1 would of course be equal to 1. Okay. If we put K1 is equal to 1 by lambda, then this lambda will go with K, and we would be close to the amplitude part of equation number 24. But we know that we are talking about E1 by 2, and for E1 theta is very small, therefore, K1 must be equal to 1. It would not be, we cannot put K1 is equal to 1 by lambda just to adhere with this equivalence. Okay. From which it follows that the Q must be equal to 1 by lambda. Why? Because when K1 is equal to 1, then what we are left with is this term, this must be equal to epsilon naught. But what is epsilon A? Epsilon A is Q epsilon naught, okay, and it was equal to rho here in the denominator, yeah, and then rho lambda, this must be equal to epsilon naught. Okay, then from here rho we will go away, epsilon naught will go away, and from here Q is equal to 1 by lambda. Okay. Therefore, if we want to adhere with this equivalence, if we want the two expression 24 and 25 to exactly say the same thing, then Q must be equal to 1 by lambda. Okay. And this is how we decided the unknown constant Q. Yeah, we initially assumed that there is some constant Q which appear in the source strength. Now, its value is decided with this equivalence. Yeah, and Q is equal to 1 by lambda. Okay. Q is now no more unknown coefficients or unknown constant. Okay, this is the first point which came out of this comparison. What is second point? Now, epsilon A rho lambda, this must be equal to epsilon, this is what is written, epsilon A rho lambda, this must be equal to epsilon naught. Keep in mind that epsilon A is the secondary wavelet source strength per unit area over the primary wavefront of radius rho. Okay, epsilon A is secondary wavelet source strength per unit area over the primary wavefront of radius rho. Okay, and epsilon naught by rho is the amplitude of the primary wave E naught rho. Okay. Therefore, the source strength per unit area epsilon A would be E naught rho by lambda, okay, which is again very much clear. Okay. This came from this relation directly. Okay. Epsilon A is equal to epsilon naught by rho lambda, and we know that epsilon naught by rho is equal to E naught rho, and with this replacement we get epsilon A is equal to E naught rho, function of rho by lambda. Okay, once we have equated the amplitude part, let us go to the phase part. Now, let us go again to equation number 24 and 25. In equation number 24, we have cos of omega t minus k rho plus r naught, while in equation number 25, we have sin of omega t minus k rho plus r naught. Okay. In equation number 24, we have cosine term, while in equation number 25, we have sine term. Okay. Pi by 2 phase difference therefore is there, and this pi by 2 phase difference between equation number 24 and 25 can be accounted for if we are willing to assume that the secondary source radiates 1/4 of a wavelength out of phase with the primary wave. Okay, this is something which is very new now. Here what is being introduced is that secondary wave source or secondary wavelets are out of phase with the primary one by pi by 2 angle. Okay, there is a phase difference between the primary and secondary radiations. Okay. If we assume that this is correct, then only equation number 24 and 25 they say the same thing, then only they will be exactly equivalent. I will talk more on this phase difference between primary and secondary source in coming lecture, but right now we will just assume that this is so. Okay. And if we assume this, then we see that this equivalence is correct. The equation 24 and 25 they are exactly equivalent and they are same. Okay, and everything is well justified. All the analysis what we did using this secondary wavelet theory, it is correct till now. Okay. This is the first introductory lecture on Fresnel diffraction, and this the mathematics which we developed, it would be used throughout in understanding the diffracting element in Fresnel domain. Okay. With this I end my lecture, and thank you for joining me. See you all in the next class.